today we'll start with phenols. So phenols are the aromatic alcohols, or you can say you all know what is phenol is. Okay. So in phenol we'll first start with the methods of preparation of phenol. The first method of preparation is method of preparation of phenol from benzyl sulfonate and sodium hydroxide. So benzyl sulfonate, that is SO3H. To prepare this we have to start from benzene, and benzene reacts with concentrated H2SO4. This was benzene sulfonic acid or benzene sulfonate. This on further reaction with sodium hydroxide, this produces SO3Na, and this reaction with 2NaOH, this produces sodium phenoxide, ONA, and upon further reaction with mild acid or weak acid, this produces phenol. Okay. This is the method of preparation of phenol from benzene sulfonate or benzene sulfonic acid. Okay. Next method of preparation is from BDC or benzene diazonium chloride. The starting material is BDC. So this BDC on reaction with water, this produces phenol. Okay. This BDC benzene diagonal chloride on reaction with water or boiling, this produces phenol. Okay. Next we will see and here there is presence of a mild acid. In reaction with water there is presence of dilute H2SO4, mild acid, it produces phenol. Okay. Next we will see, if you see the reaction of benzyl diazonium chloride or the production of phenol from benzene diazonium chloride, it is carried out in acidic medium, because if we do not carry this reaction in acidic medium, this benzene diazonium chloride will undergo coupling reaction with phenol. If you see the coupling reaction, phenol, this will form coupling product phenol, which is orange dye. Okay, so to prevent this from coupling, this is carried out in acidic medium, so that the phenol produced is remain protonated. So the coupling does not take place. Okay. So next method for preparation of phenol is decarboxylation reaction. Okay. The decarboxylation, you see COO and if we react this with NaOH plus CaO, this will produce phenol from CO2 plus CO2 plus S2. So this produces CO2 plus, actually it doesn't produce CO2, this CO2 reacts with sodium to produce Na2CH. Okay. Next is the production of phenol from Grignard's reagent. If we react phenyl magnesium bromide MgBr with oxygen, this will produce OMgBr, and upon hydrolysis this produces phenol. Okay. Next method for preparation of phenol is from cumin. What is cumin? This compound is known as cumin. CH single bond CH3 single bond CH3. This compound is known as cumin. So to produce cumin, first we have to react benzene. So this method is from cumin. So to produce cumin, we have to react benzene with propene in presence of H3PO4, a strong acid. So what happens in this method? This is first protonated. For the production of secondary carbocation, and then benzene reacts with this secondary carbocation as an electrophile to produce cumin. And this cumin reacts with oxygen, this produces cumin hydroperoxide. This cumin hydroperoxide upon heating produces phenol and acetone. Okay, this is another method of preparation of phenol from different methods. Okay, next method for the preparation of phenol is one from benzene. When benzene reacts with 2HCl, oxygen in the air in presence of CO2, CO2 produces chlorobenzene. And chlorobenzene reacts with water in presence of SiO2 at extreme condition 800 degree Kelvin to produce phenol. Okay. And next one is this modern method is used nowadays in the laboratories, or you can say industrial process. These are some industrial process for the preparation of phenol. This one is when benzene reacts with oxygen in presence of V2O5, that is vanadium pentoxide. This produces phenol. This method is used in industrial processes for the production of benzene. Okay. Next, we'll see after the preparation. We'll see the physical and the chemical properties. The physical properties. First of all, these have intermolecular hydrogen bonding. All the phenol molecules, they have intermolecular hydrogen bonding like this. If we can see C6H5OH. So all the molecules here, this oxygen, this hydrogen have intermolecular hydrogen bonding. Okay. And if you consider the solubility in water, this phenol is partially soluble, slightly soluble in water due to hydrogen bonding between water molecule and the phenol molecule. Like if you can see in the water molecule, this oxygen and hydrogen are being intermolecular hydrogen bonding. That's why phenol is little soluble in water. Okay. Next, in the chemical property, we see the acidic nature of phenol. We see phenol is acidic in nature. So if you see the acidic strength also, it is less acidic than water but more acidic than acetylene, or you can say ethyne. More acidic than ethyne but less acidic than water. We can know the acidic nature, like acid have a property, when acid react with metal, it produces hydrogen gas. So if we consider reacting this phenol with sodium, this produces peroxide plus hydrogen. I will know there is production of hydrogen gas because there is production of epoxy. Okay. So the phenol is acidic in nature. Okay. So we have already known the phenol is acidic nature. To know if it is acidic, we react this with metal and like alkali metal, and it produces hydrogen gas. So if anything react with metal and produces hydrogen gas, that means it is an acid. Okay. This property of phenol matches with the property of an acid. Okay. Next we will see this phenol when we mix this in water or in aqueous solution. This produces phenoxide ion plus H plus. Okay. Another we can say that when any substance produces H plus one ion in aqueous solution, this is also acid. So this produces H plus ion. So this is acid. Now another concept that is used in there are many theories for acid-base concept: Arrhenius theory, Bronsted-Lowry theory, and Lewis acid-base theory. You see, Bronsted-Lowry theory, if this is an acid and this produces H plus ion, so after production of H plus ion, the remaining thing will be conjugate base. The more stable the conjugate base, stronger will be acid. Okay. The maximum stability of the conjugate base, more stable, stronger will be the acid. So if we account for the stability of phenoxide ion, this phenoxide ion is stabilized by resonating structures, or we can say this is stabilized by 5 resonating structures. We see those resonating structures as this is phenoxide ion, transfer of electron, negative charge. This negative charge will delocalize, and we will see the 5 resonating structures. This electron transfers, formation of negative charge at ortho and para positions. Here this phenoxide ion is stabilized by 5 resonating structures. So this conjugate base, that is phenoxide ion, is more stable. So as the conjugate base is more stable, phenol will be acidic. Okay. This phenol, another thing we can say about the phenol and the phenoxide ion, that the phenoxide ion is more stable than phenol also. Like if you compare the stability between phenol and phenoxide ion, the phenoxide ion will be comparatively more stable than the phenol. So I hope you have studied this phenoxide ion is more stable than phenol in the +2 chemistry. But the reason for that is, if you see the resonating structure of phenoxide ion, there is formation of carbon oxygen double bond and one negative charge appearing on the aromatic ring. But if you see the resonating structure of phenol, so there is generation of one positive charge and one negative charge. So there will be some amount of energy required to separate two charges, as there are opposite charges. So there will be some energy required for the separation of these charges. So if some energy is required, the energy for the phenol will be higher than energy for phenoxide ion, and we know that higher the energy higher, stability loss. Okay, as high as the energy will be, as low as there will be stability. Okay, next we will see for acidic in nature. We will see, like, okay, in acidic in nature, there is an influence of substituents on the acidity. Like if we compare, there are two substituents, like two categories of substituents. One which gives +I, effect and one which gives minus I effect. This plus I group that decreases acidity, and this minus I group increases acidity. Okay. Like if we compare the acidic strength of phenol para-nitrophenol and para-methylphenol, this is known as cresol, para-cresol. So we name these compounds as A, B, C. The order of acidity will be, most acidic will be B, then A, then C, because here is the attached ring is producing minus I effect. Minus I effect, that means it is electron withdrawing in nature, as this withdraws electron from phenol. There is easy removal of H plus ion, and here this is plus I effect or electron donating group, which increases the electron density, hence the removal of H plus is not easier, it is more difficult. Okay, the order of acidity will be, first will be para-nitrophenol, then there will be phenol, then there will be para-cresol or para-methylphenol. Okay. Next we will see, if we compare like the acidity of orthomethylphenol, then para-methylphenol, then metamethylphenol, A, B, C. Order of acidity will be, highest acidity will be C, then B, then A. Okay. So we'll see the explanation for this. The explanation for this will be, the phenol is ortho-para directing in nature. Okay, we can see phenol. If we see the resonating structures in phenol, there is appearance of negative charge or increase in electron density at ortho, para and ortho positions. Okay, so the plus I group present in ortho and para positions will affect more the phenol, or they will increase more electron density on phenol. Significantly, the meta group will not be. So this will make less electron donation as compared to B and A. And if we compare A and B, okay, so one is at ortho position, one is at para position. So here this is distance dependent. So this CH3 at ortho position is near the OH group, so this will increase more electron density as compared to the para group, because the para group is at higher distance than the ortho group. This will make the highest increase in electron density, this will be medium, and this will be the least electron increase in electron density. So the order of acidity will be C, then B, then A. Okay. Next in the reaction we will see the Fry's rearrangement. Okay. The Fry's rearrangement, if you see the reaction for Fry's rearrangement, this is a name reaction. When this phenyl ester, sorry, this phenyl ester reacts with AlCl3. This produces phenol and one acyl group in the ortho position. Okay, here the Lewis acid AlCl3 plays a very important role. Okay, so in we see the reactions. In every reaction, hydrolysis is not mentioned, but it is always there. Okay, so if you see the mechanism, the first step, we know that the AlCl3, this is Lewis acid, that means AlCl3 have a vacant p orbital. Okay, so due to presence of this vacant p orbital, this will presence of vacant orbital, this should accept one electron. Okay, in the first step, this oxygen will donate electron to aluminum, and there will be formation of one complex. As it donates electron, it becomes positively charged. Aluminum accepts electron, so it becomes negatively charged. Okay. The next step, okay, one R group is also attached. The next step, there is migration of this electron to aluminum, and there will transfer of electron here to here. Okay. So there will be formation of O, then AlCl3 minus plus RCO electrophile. Okay. The next step, aromatic attack to the electrophile. So there will be formation of C double bond O R and OlCl3 minus. Okay, and this plus, and then there will be aromatization. So formation of COR and OlCl3 minus. Okay, in the next step, upon hydrolysis, this will break down and there will be formation of OH, C double bond OR plus LCl3. The Lewis acid will come back. Okay, this is Fry's rearrangement. Okay, the next class we will see electrophilic reactions of phenol and different name reactions, and there are some other name reactions we'll see in the next class. Okay, if you have any doubt, let me know in the comment section. I'll try to solve them.